In module 2 of chapter 10, we shall learn about mappings on surfaces and spaces. In this module, we shall learn two important mappings. The first one is isometric mapping and the second one is conformal mapping. Isometric mapping preserves the distance between 2 points. Conformal mapping preserves the angle between 2 arcs. So, these two mappings are very important concept in the field of geometry. So, let us learn about the isometric mappings and conformal mappings. And here we shall see that for isometric mappings, the first fundamental forms, that is or the coefficients of first fundamental forms are equal, and the Gaussian curvatures, the geodesic curvatures are also equal. These things we have learned in our previous chapters. So, here we shall see that for isometric mappings, the coefficients of first fundamental forms are equal, and so the Gaussian curvatures are also equal for two surfaces, and the geodesic curvature of the corresponding curves are also equal. But for the conformal mapping, we shall see that the coefficients of first fundamental forms are proportional. So, let us start the isometric mapping. So, in module 2 of chapter 10, we shall learn about mappings on surfaces and spaces. Here we have two learning objects. The first one is isometric mapping and the second one is conformal mapping. So, we shall learn about these two type of mappings in this module. Now, let us see what is isometric mapping. Now, two surfaces S and S star are said to be mapped upon one another if there exists a one-to-one correspondence between their points. So, it is very elegant from this definition that when S and S star have the relation by a mapping. Now, let the equation of S be R equals to R u v and S star be R star, that is R star u 1 v 1. These are the two equations of the two surfaces. Then a mapping of a region of S on a corresponding region of S star will be set by functional relation. Now, let this is the functional relation, it is defined in this way: u 1 equals to u 1 of u and v, and v 1 is also a function of u and v, the v 1 of u and v. So, u and v 1 are both the functions of u and v. The u and v 1 are single valued functions with continuous partial derivatives such that Jacobian does not vanish, because to get the inverse relation we need that Jacobian should not vanish. Now, such mappings are called allowable mappings. So, equation of S star can be written in this form R star u v, because they are functionally related with u and v, the variables u and v. So, R star also can be expressed in a function of u and v. Where the points of S and S star correspond under the mapping given by 18. Now, these mappings preserve some geometrical properties. Firstly, we deal with isometric mapping, which preserves the distance and angle both when every arc is mapped from S to S star. So, isometric mapping preserves distance and angle both when every arc is mapped from S to S star. So, we can define in this way, an allowable mapping from S to S star is said to be isometric if the length of any arc on S star is the same as that of its inverse image on S. So, this inverse image is established by that the Jacobian does not vanish. So, we now prove this theorem that an allowable mapping between two surfaces S and S star is isometric if and only if at corresponding points of S and S star, when referred to the same coordinate systems on S and S star, the coefficients of the first fundamental forms A alpha beta and A star alpha beta are same, where alpha beta is running from 1 and 2. We know that for surfaces the alpha beta runs from 1 and 2. So, for isometric mapping, we shall prove that the coefficients of the first fundamental forms A alpha beta and A star alpha beta are same. Now, let us see the proof. Let U1 U2 and U1 star U2 star be the coordinates of S and S star respectively. Now, since these two coordinates have functional relation and assume to be same, so we can write U1 star equal to U1 and U2 star equal to U2. So, if U alpha is written as x alpha t is an arbitrary arc C on S, then its image C star is given by U star alpha equal to x alpha t, where 0 less than equal to t less than equal to t1 and alpha is running from 1 and 2. Now, as we have seen that U1 star equal to U1 and U2 star equal to U2. So, these two are same. So, if we take the arc length on C, so it will be S T0, we can write 0 to T0 square root of A alpha beta dx alpha dt dx beta dt whole dt. And on C star, A star is 0, the arc length on C star, it will be given by this one 0 to T0 root over A star alpha beta dx alpha dt dx beta dt and whole dt, the integration with respect to dt. So, if every point P of S and its image P star of S star, we have A alpha beta equals to A star alpha beta. Then if we assume this one A alpha beta equals to A star alpha beta, then S T0 will be equal to S star T0. So, if A alpha beta equals to A star alpha beta is assumed, then we have seen that the arc lengths are same, S T0 equals to A star T0. Now, conversely, we assume that the arc lengths are same, S T0 equals to S star T0 holds for every value T0 belongs to 0 to T1, and the equation 20 and 21 are equal. So, the previous equations are equal. Then integrands are will be also equal. Now, since this relation holds S T0 equals to S star T0, so the integrations are equal, therefore, the integrands are also equal, and thus A alpha beta is equal to A star alpha beta must hold for alpha beta equals to 1 2. So, thus the theorem is proved. So, we have seen that for isometric mapping the arc lengths are equal and therefore, the coefficients of the first fundamental forms are also equal. For example, let us see the cylinder with equation R u v equal to cos u sin u v. The parametric equation of a cylinder is given by this, and if it is mapped isometrically onto a strip of the plane u star v star equals to u star v star 0, as it is a plane. So, the third component is 0, and this one is given by the mapping u star equal to u and v star equal to v, and 0 less than equal to u less than equal to 2 pi. So, this is the isometric mapping given by this one u star equal to u and v star equal to v, and the cylinder is mapped isometrically onto a strip of the plane. Here we can easily verify that A11 equals to A11 star equals to 1, A12 equals to A12 star equal to 0, and A22 equals to A22 star equal to 1, and so the mapping is isometric. Here the coefficients of the first fundamental forms are equal for both the surfaces. So, the mapping is isometric. Now, we state another important theorem, that isometric surfaces have the same Gaussian curvature at corresponding points, and corresponding curves on those isometric surfaces have the same geodesic curvature at corresponding points. So, this is a very important theorem, and it follows easily from theorema egregium of Gauss, which was proved earlier in chapter 9, that according to the theorem of Gauss, the Gaussian curvature depends only on the coefficients of the first fundamental form, and which are invariant under isometric mapping. Just we have seen that they are invariant under isometric mapping. So, Gaussian curvature at corresponding points of isometric surfaces are same. Similarly, geodesic curvature also depends only on coefficients of first fundamental form only. So, geodesic curvature of the curves on the isometric surfaces are same at corresponding points. But we have to note that isometric surfaces must necessarily have the same Gaussian curvature at corresponding points, but the condition is in general not sufficient. That means, Gaussian curvature may be same, but they may not be isometric surfaces. For example, we can take this logarithm curve x 3 equal to log x 1 is rotated about x 3 axis, and it generates a surface of revolution whose parametric equation will be this one, R u v equals to u cos v, u sin v log u for u greater than 0. Now, for this we can find the Gaussian curvature. This one is equal to minus 1 by 1 plus u square whole square. In our previous chapters, we have learned how to find the Gaussian curvature. So, by considering those things, we can find the Gaussian curvature, and we have obtained that Gaussian curvature is coming to this one. again for the right helicoid, we have obtained in our earlier chapter the intrinsic geometry of the right helicoid. We have obtained the Gaussian curvature and many other things on right helicoid, and we have seen that for right helicoid, if the equation is expressed in this form, the Gaussian curvature is this one, minus 1 by 1 plus u star square whole square. So, for the mapping u star equal to u and v star equal to v, the Gaussian curvature for both the surfaces is the same, but the mapping is not isometric, because for the first surface the first fundamental form is coming to this one 1 plus 1 by u square du square plus u square dv square, but for the second surface for the right helicoid we have the first fundamental form is this one. So, here A alpha beta, that is the coefficients of the first fundamental forms for both the surfaces, are not equal. So, A alpha beta is not equal to A star alpha beta. So, the condition is sufficient only for the surfaces of constant Gaussian curvature. So, if the Gaussian curvature is only constant proper, then the sufficient condition holds, otherwise the condition is not sufficient in general. In first section of module 2 of chapter 10, we have learnt about isometric mapping. We have seen that for isometric mapping between two surfaces, the coefficients of the first fundamental forms are equal. We have also seen that Gaussian curvatures of two surfaces are also equal, and the geodesic curvature are also equal for corresponding curves. In the next section, we shall learn about conformal mapping. Conformal mapping was given by Subest in the year 1788. Conformal mapping is a angle preserving mapping, and we will prove that for conformal mapping the first fundamental form are proportional, rather the coefficients of the first fundamental forms are proportional. And lastly, we have also see that the expressions for conformal curvature tensors for n dimensional space and also for the 4 dimensional spaces. So, now let us study the conformal mapping. So, in section 2 we shall learn about conformal mapping between two surfaces, and at last we shall also see some expressions for spaces. Now, just I have mentioned that the name conformal was introduced by Subest in the year 1788, and after him many other mathematicians like Euler, Lagrange and Gauss developed the systematic theory of conformal mapping. An allowable mapping from a surface S to another surface S star is called angle preserving or conformal if the angle between two intersecting curves at a point P of S is equal to the angle between two intersecting curves on S star at P1, which is the corresponding point of P. So, this is the definition of the conformal mapping, which preserves the angle from one surface or one space to other space. Now, we know that the angle theta between two tangent vectors on two arcs on a surface S can be expressed in the form cos theta equals to A alpha beta lambda 1 alpha lambda 2 beta. So, if we break this one, that means alpha beta is running from 1 and 2. So, we will get this one A11 du1 ds1 del u1 del s2. For the second surface, we have considered S2 as the arc length, and for the first one it is S1 for the first surface. So, the above expression is coming like this. Where lambda 1 alpha is du alpha ds1 and lambda 2 beta has the components del u beta del s2. Now, as on a surface, the first fundamental form is same. So, we can consider ds1 equals to del s2, and so we can write only ds or del s. Now, angle theta star of A star also can be written in the same manner, and if we consider the pair where del u1 is arbitrary and del u2 equals to 0 for both surfaces, then we can have theta equals to theta star. If we consider this one theta equals to theta star, then we shall get this one A11 du1 del u1 plus A21 du2 del u1 by ds root over A11 del u1 square, and similarly the next one. So, from here if we just break these relations, we get this relation. Now, this equation must holds for all directions of du2 du1, and so we have root A11 du1 ds equals to root A11 star du1 ds star. And therefore, we can write this one also, the second part A21 by root A11 du2 ds equals to A star 21 by A11 star du2 ds star. So, by these two relations we get ds star by ds equals to root A11 star root by root A11, and that is equals to A star 21 root A11 by A21 root A11 star. Now, from 24 we can see that ds star by ds equal to alpha, and it is independent of du2 d1 and depends only on the point u1 u2. So, we can write ds star equal to alpha ds, where alpha is the functions of u1 u2. So, A11 star will be equals to alpha square A11, A21 equals to A12 equals to alpha square A12 star equal to A21 star, and A22 star will be equals to alpha square A22. Thus, for conformal mapping we have seen that A star alpha beta equals to alpha square u1 u2 A alpha beta, where alpha beta is running from 1 and 2. That means, the coefficients of the first fundamental forms between these two surfaces are proportional. Now, conversely, if 26 hold, then obviously we can see that cos theta star equal to cos theta. That means, the mapping is angle preserving, and so it is conformal. So, we have seen that for conformal mapping the coefficients of the first fundamental forms are proportional, If the value of alpha equals to 1, then this will be the isometric mapping. That is why isometric mapping also preserves the length and as well as the angle. So, we can state that an allowable mapping from a surface S to another surface S star is conformal if and only when on S and S star the same coordinate system have been considered, the coefficients of first fundamental form A alpha beta and A star alpha beta are proportional, that is A star alpha beta equals to alpha square A alpha beta. So, every isometric mapping is conformal, as a corollary we can get. Now, this conformal mapping or transformation can be defined on an n dimensional space in a similar way, and in that case the Riemann curvature tensor Rijkl and conformal curvature tensor Cijkl have the relation, this one Rijkl is the Riemann curvature tensor and this Rjl, Rik etc. are the Ricci curvature tensors and Gik are the metric tensor. So, this is the relation between the conformal curvature tensor and the Riemann curvature tensor if we consider an n dimensional Riemannian space. R is the scalar curvature, Gij, Rij are the Riemannian metric and the Ricci tensor respectively. Now, conformal curvature tensor cannot be defined for n equals to 2, it is defined for n equals to 3 and above, but for n equals to 3 we can easily see that Cijkl is equal to 0. So, a 3 dimensional space is conformally flat. When n equals to 4, that is for 4th dimension, because it is used for general theory of relativity, and in that case the equation becomes this one Rijkl equals to Cijkl plus half of Gik Rjl plus Gil Rik minus Gil Rjk minus Gjk Rik plus this one R by 6 Gil Gjk minus Gik Gjl. So, for n equals to 4 we get this relation between conformal curvature tensor and the Riemann curvature tensor. Now, this expression Cijkl is given by Well, and so it is called Well conformal curvature tensor. So, in module 2 of chapter 10, that means some applications of differential geometry, we have learned two important mappings, that is isometric mappings and conformal mappings. We have seen in the first section that for isometric mappings the coefficients of first fundamental forms are equal, and so the Gaussian curvatures for the two surfaces are also equal, and the geodesic curvature for the corresponding curves are also equal. In the next section, we have learnt about conformal mapping, and we have seen that for conformal mapping the coefficient of first fundamental forms between two surfaces are proportional. And lastly, we have also seen the expressions for an n dimensional Riemannian space. We have seen the expressions for the conformal curvature tensor in terms of Riemann curvature tensor, Ricci tensor and the metric tensor. With this we end this module.